Hey everybody, Dr. A here, and in this video we're going to be providing some background information on the dot product. So let's go ahead and get started. Study is on applications of the dot product. Now, from a previous class, maybe physics or a math course, you may have learned a little bit about what the dot product is, more from a mathematical perspective. Here, we're going to review that a little bit and then get into some applications as they pertain to statics. So, if you recall, the dot product is actually a special case of matrix multiplication. And the most common forms of it are as follows. If you have a vector A and you say vector A dot with some other vector B, we typically write that as the magnitude of A times the magnitude of B times cosine of theta, where theta is the angle in between the tails of vector A and B. So that would be like if we have some vector A right here, and then we have some vector B right here, and theta is the angle in between them, okay? Now, another way to express the dot product that you may be familiar with is when we say vector A dotted with vector B, that is also equal to the components, the corresponding components of A multiplied by the corresponding components of B and then added all together. So for example, if vector A had component A1, A2, A3, all the way to AN, and you dotted that with vector B, which maybe had component 1, B1, B2, B3, all the way to Bn, what that gives us is A1 times B1 plus A2 times B2 plus A3 times B3 plus plus AN times BN for however many components each of those vectors have. Now, again, you may remember that from mathematics. In statics applications, we're really just going to be dealing with 2 and 3 dimensional vectors. So for our statics applications, we're really only going to have either like 2 components for each of our vectors or 3 components for each of our vectors. But in general, you can have as many components for a vector as you want. Another thing to keep in mind is the dot product yields a scalar result. So if you look at both forms of the dot product that we've written here so far, we have the magnitude of A times the magnitude of B times cosine of the angle in between. This right here, AB cosine theta, that is just a single number. It's a scalar. It itself is not a vector. And then the same thing goes for the other form of the dot product that we've drawn here. When we perform each of these multiplications and then we add each of these terms together, the final result is a single number, not a vector. Okay, so again, the dot product is always going to yield a scalar result. Now, here's the next thing to keep in mind. If A dot B equals AB cosine theta, and also A dot B equals the product of the of each of the components and then add them together, then guess what you can set equal to one another? You can set equal AB cosine theta and this product right here. So let's do that. Let's say that magnitude A times magnitude B times cosine theta equals A1 B1 plus A2 B2 plus all the way to AN BN. Okay, now what can we get out of this little relationship that we just set equal to one another from each of the dot product expressions? Well, we can actually calculate the angle in between these two vectors if that's what we're interested in. So we can say theta turns out to be the arc cosine of A1, B1 plus A2, B2 plus dot, dot, dot plus AN, BN, all divided by the magnitude of A times the magnitude of B. So this is a handy form of this relationship if what you're looking for is the angle in between these two vectors A and B. Okay, so again, none of this is probably brand new to you because I feel like that you've probably seen the dot product a little bit in a math course or physics, but maybe this will refresh your memory on some of this material. Now, another interesting property that that is inherent with a dot product that can help you kind of realize some relations between vector A and vector B is the following. Now it's a big if you dot vector A with another vector B and the result is 0, then what does that mean? Well, if A dot B is 0, then it turns out vector A and vector B are orthogonal with each other. Okay, and remember orthogonal means perpendicular, right? They're perpendicular to one another. So how do we know that? Well, you could just memorize it, but let's talk about why a little bit more. Here's why. I'm going to say the reason is this, dot, dot, dot. If A dot B equals AB cosine theta, and let's say that does turn out to be 0, then what are we really saying? We're really saying AB cosine theta equals 0. Now remember, A and B are the magnitudes of vector A and vector B. So A is a scalar and B is a scalar. So when you divide this out, you're just left with cosine theta equals 0. And so how do you solve for theta in this situation right here? Well, if you remember your very basic trigonometry, theta would be the arc cosine of 0 degrees, which is just what? It's pi over 2 or 90 degrees. Hence, vector A and vector B would then be perpendicular to one another. Okay, so that's another piece of useful information that the dot product can kind of illuminate for us for specific problems. Okay, so let's summarize the laws of operation of the dot product. Okay, the first law is called the commutative law. Commutative law. Now, commutativity in mathematical operations means that when you multiply two things together, then it's equal to the same thing as if you multiplied them in the other order. So A times B equals B times A, or in more specifically, A dot B equal, look at that. I said B dot B, that's not right. B dot A. Sorry, back up 1 second. So what we're saying is A dot B is the same thing as B dot A, okay? So commutative law holds, and that's also because the dot product yields a scalar anyway. So it's the idea of 2 times 3 equals 3 times 2, for example. Now, remember, in general, for general matrices, commutativity is not true, okay? But for the dot product specifically between vectors, it does hold true. All right. The next important law is scalar multiplication. Okay. Scalar multiplication. So what we're saying is if we have a scalar little a and we multiply that by A dot B, vector A dot vector B, this would be the same thing as if you grouped little a times vector A and you dotted that with vector B. And that would also be the same thing as if you grouped vector A times the grouping of scalar little a times vector B. And also that could also be the same thing as vector A times vector B times A with a right multiplication. So scalar multiplication, all it's saying is if you're dotting two vectors together, but you also have a scalar hanging out in there that you're multiplying in, you can multiply those essentially in any order, okay? And we also have the third law, which is the distributive law. Distributive law, that's a B right there. So what the distributive law says is if you have vector A dotted with vector B plus vector C, then this would be the same thing as vector A dotted with vector B plus vector A dotted with vector C. Okay, so that's just a regular law of distribution. All right, so that's a nice little overview of you know, how the dot product works. Hopefully this isn't, you know, brand new to you, but if it is, that's okay. That's why we went over it. So let's get into applications to statics now. All right, applications in statics. So most often you're going to use the dot product to compute components of a vector that are parallel and perpendicular to an axis. So a lot of times in both structural and mechanical systems, we have members that are inclined on some kind of specific axis that has its own you know, angle orientation. And we often are interested in the force components acting parallel to a particular axis as well as perpendicular to that particular axis. And that's where we can apply the dot product to help us investigate those components. So let's consider the following. Let's say that we have this axis right here, okay? And let's say that we're gonna call this maybe the, how about we call it the A axis, okay? And let's say that the A axis is defined by the unit vector u sub A. All right, so we'll make a note here. U sub A defines the A axis. Now again, this A axis could be oriented anywhere. I just happen to draw it, you know, increasing, you know, pointing in this particular direction. This A axis could be any axis oriented in any direction, okay? So now let's say that you have an applied force acting like so, all right? Let's call this vector force F. So what we may be interested in is the components of vector force F that are parallel to this axis right here, as well as the component that is perpendicular to this axis right here, all right? So I would call this component that's parallel to this A axis, I'm gonna call that, how about vector F sub A, just because it's sub A because it's along the A axis that I just talked about. And then I'm gonna call the perpendicular component vector F, and then I'll put a little perpendicular symbol right there, okay? And again, this is forms a right angle right there, hence perpendicular, okay? Now let's say that the angle that our vector force F is making with this axis, with this A axis, let's say that that is an angle theta right there, okay? So again, we're going to say let theta be the angle F makes with the A axis, okay? So here's how we can kind of piece things together and relate it to the dot product, all right? The first thing I'm going to do is I'm going to say, well, I can kind of investigate this little right triangle that is formed between the A axis and F, okay? And so if I try to investigate this little right triangle, what can I put together from there? I can say that cosine of theta equals the magnitude of FA. So I can say FA, magnitude of it, over the magnitude of F itself. And remember, my notation says that, if I want to, I could put bars around this if I wanted to. That's okay. Or I can not put the vector hat and also not put the bars. So however you want to write it is fine with me. But note that these are magnitudes of each of these vectors. Okay. Now I can do a little bit of rearranging, and I can get magnitude of FA is equal to magnitude F times cosine theta. All right, no question there. Now, if you remember from some previous videos, where does the usefulness of a unit vector come from? Okay, this unit vector U sub A is defining this A axis as we said a few minutes ago. So I can express FA as a Cartesian vector by saying the following. I can say that Cartesian vector FA, again, this is the component parallel to the a-axis, is equal to its magnitude FA times that unit vector defining the a-axis. Okay, that line shouldn't be new to you. All right. So that's what we have so far. Now, what do we know about the magnitude of FA? Well, we just figured out that's F cosine theta. So I can further write this as the Cartesian vector FA is F cosine theta times the unit vector UA. All right. Now, what do we have here? Well, if you look very carefully here, we can start seeing where this is kind of relating, or we're kind of tiptoeing into the application of a dot product. Okay, so we can also say that the magnitude FA is equal to vector F dotted with the unit vector U sub A. Now, why can we say that? Well, remember, what is the magnitude of the unit vector for any unit vector? Well, that's just 1.0. Remember, that's part of why it's called a unit vector. All right. So here are some of the cool things we can end up piecing together. We can say that vector F dotted with the unit vector defining axis A, little a right there, is equal to F times 1 times cosine theta, okay? And that ends up also equaling the magnitude little FA, all right? What else can we kind of piece together? Well, this so far has all been with respect to this parallel component right here. What about the perpendicular component? What can I say about F perpendicular? Well, we can also say the following. We can say vector F is equal to vector F sub A plus vector F perpendicular. Okay, and then we can do a little bit of rearranging here, and we can say the perpendicular component, which we may also be interested in statics, is equal to vector F minus vector F sub A. Okay, so here's how we piece together and get that perpendicular force component. What else can we end up saying? We can also say the following. We could say theta equals arc cosine of vector F dotted with the unit vector defining axis A divided by the magnitude of vector F times 1, right? So all of this comes from an application of the dot product that we discussed earlier, right? We dot these two vectors together, and then we divide by each of their magnitudes multiplied together. So this is kind of like from earlier. This is like vector A dot vector B divided by magnitude of A times magnitude of B, right? We talked about that way up here, right? So that's an application of this. There's theta, no question. And then we can say, and this perpendicular force component ends up equaling the magnitude of F times the sine of theta, all right? We can also use the Pythagorean theorem, and we could say the perpendicular component of F is equal to, this should be a magnitude here, sorry, get rid of that vector hat. The magnitude of F perpendicular is equal to magnitude of F squared minus the magnitude of FA squared. All right. So again, this has been a review of the dot product, a review / overview of the dot product, and some ways we can apply it to statics. And I think in the next few examples, when we see some numerical examples of this, this may become a little more clear to you. I also encourage you, as always, read the textbook. Read the textbook on the section in chapter 2